Hello and welcome to another slide video from the Cornish Radio Amateur Club, and today we're going to look at radio waves. This slide video is part of the background series, so it's not really aligned to either foundation, intermediate or advanced, but it can perhaps be of use to any of them. So let's have a look about radio waves. Well, first of all, they were first postulated by Maxwell, and they were demonstrated to work by Hertz. He managed to make a spark jump remotely. They are produced naturally by lightning storms at extremely low frequency and pulsars at ultra high frequency. They travel in a straight line unless they're affected by something. If you had any radio wave in space and sent it off on its way, it would go off in a straight line unless something changes its direction. And they are to varying degrees attenuated, that means reduced in level, by liquids, solids and gases. So they travel best in a vacuum. And they always get weaker with distance from the source, as they naturally spread out. So no matter how you focus them, whether you focus them with a dish antenna or something like that, a bit like light, as it spreads out, just the action of spreading out causes it to weaken in intensity. And radio waves are called transverse electromagnetic waves. So what is a transverse electromagnetic wave? Well, first of all, to say that we do not need to know or understand any of this for the foundation examination. We do not need to know anything about wave theory at all. But it is useful to frame the context of what we do need to know. So in the foundation examination, we need to understand the relationship between frequency and wavelength. And this will give you some background, although, as I say, you don't have to know this. So a radio wave is a transverse electromagnetic wave. Let's have a look at, first of all, the transverse wave aspect of it, and then in a minute we'll have a look at the electromagnetic aspect of it. So a transverse wave is a wave in which the medium vibrates at right angles to the direction of propagation. And here we've got a small graphic, a small animation on the right hand side, and there you can see the oscillation happening up and down and the propagation happening left to right. Let's have a look at that again. The oscillation up and down and the propagation left to right. So this is a wave in which the medium vibrates at right angles to its direction of propagation. Or you could say it the other way around. You could say the direction of propagation is at right angles to the vibration. Let's have a look at the electromagnetic part of it. Well, in an electromagnetic wave, we have electric and magnetic fields. So you'd expect that from the word electromagnetic, electric and magnetic fields. And the abbreviation that's used for electric is a capital E, and for the magnetic field, a capital H. So we can say the E and H fields are right angles to each other and the direction of propagation. So with a transverse field, we have the medium vibrating at right angles to the direction of propagation, but now we have two fields, both at right angles to the direction of propagation and at right angles to each other. Now this is a little bit difficult to represent, but let's see if we can do it. That is the direction of propagation, and the velocity of propagation depends on the medium. And for radio waves, there's not much difference between vacuum and air. There's only a negligible difference, so we don't normally take it into account at all. Now, here we have the electric field, and you can see the little vector diagram or phasor diagram at the top showing the phasor for the electric field going from the bottom to the top, in other words a vertical phasor, and that is at right angles to the direction of propagation. And now we're going to draw in the magnetic field, and the magnetic field is coming in and out of the page, and that is also at right angles both to the direction of propagation and to the electric field. So we've ended up then with a electromagnetic field. It has the E and the H fields at right angles to each other and to the direction of propagation. And lambda there, which is the abbreviation for wavelength, shows one cycle both of the E and of the H field. Now the relationship between the E and the H field is constant, and one does not exist without the other in a radio wave. It's impossible to have a radio wave with only an E field or with only an H field. It is possible to have only an E field or only an H field, but if they are coherent, in other words at the same frequency and both there together, then it is a radio wave. Otherwise it's simply an electric field or a magnetic field, and they don't propagate very far. It's this co-relationship which makes radio waves go further. So this is an electromagnetic wave, and by convention we label the polarization of the radio wave the direction of the E field. So if the E field is going vertically, then we say it is a vertically polarized radio wave. If you rotated that diagram through 90 degrees along its longitudinal axis, then you would have a horizontally polarized radio wave, and then the blue marks would be then going vertically. The H field would then be vertical. Now let's have a look at some waves, but because we can't visualize radio waves directly, let's have a look at the Slinky toy. Right, here we have a Slinky toy, and the hand, if you like, is the oscillator. And we're sending a single wave down through the Slinky toy. And let's have a look at that in slow motion. There goes the wave, and that is the velocity of the wave in its direction of propagation. As an aside, and not for discussion now, we're also seeing a reflected wave coming back, but that's irrelevant to what we're talking about at the moment. So there's the wave travelling along. Let's see if we send a single wave. There's a reflected wave again. Now if we provide a transverse wave to the Slinky toy, we get about one wavelength over the length of the Slinky toy. That's what you can see about there. And you can see that the field there, and perhaps you could represent that could be the E field, is going from positive to negative to positive to negative. Now we had two Slinky toys and managed to do them at the same time, showing the H field. Well, we wouldn't be able to do that, they'd get tangled up, but then it would better represent a complete electromagnetic wave. But here we have a transverse wave being propagated in a Slinky toy. Let's have a look at that as a graphic instead. So this is a fairly low frequency oscillation, and you can see this is what happened with the Slinky toy. The hand moved backwards and forwards in a transverse manner and caused these oscillations then on the Slinky toy. And what we saw there was a velocity v of the waves being propagated from left to right, and a fairly long wavelength. Let's have a look at it again. This time we're showing continuous oscillations. And this is in real time, and then if we increase the frequency, you can see that the number of cycles shown on the Slinky toy is far greater. So that was approximately twice the frequency. So what we saw there was the same speed of propagation from left to right, but with the hand moving faster, we get more cycles of oscillation on the floor. In other words, we're seeing a shorter wavelength for the same velocity. So with a low frequency oscillator, we were seeing this, and with the double frequency oscillator, we were seeing that. And we show that as a graphic. There it is, the low frequency oscillator at the top, and the double frequency oscillator on the bottom. And you can see then, for one wavelength, one lambda of the low frequency oscillator, we had 2 lambda, or 2 wavelengths, or 2 complete cycles on the floor from the double speed oscillator. So you can see that the wavelength then is linked to the frequency. And so we can say then, for transverse waves, you can see at the top there 1f and 2f, the frequency, the wavelength, and the velocity of propagation are linked. So we can say that higher the frequency, the shorter the wavelength for the same velocity. Now, if we slowed the velocity down in the Slinky, you can imagine that the wavelength would also slow down. I beg your pardon, the wavelength would become shorter because the oscillations would bunch up on the floor. So the relationship then is lambda equals v over f. The wavelength is equal to the velocity over the frequency. Now, like all of these 3 variable equations, a bit like v equals IR, I equals v over r, and r equals v over I, we can use the triangle to solve for any of the 3 variables. So a bit like Ohm's law triangle and the power triangle, here we've got the frequency and wavelength triangle. So let's try them out then. V equals f lambda, lambda equals v over f, and f equals v over lambda. So we can always reproduce those 3 forms of the formula using the triangle. This avoids us having to do the algebra. Now, going back to discussing Slinky waves, with Slinky waves, if you like, they are transverse waves, and the velocity depends on the medium through which the wave is propagated. So I think the velocity for a Slinky wave on tiles is about 3 meters per second. That's a bit of an estimation, but it's something like that. But perhaps on a surface with more friction, it would only be 2 meters per second. So if we were to do some calculations regarding frequency and wavelength for Slinky waves, we would need to know the velocity and use the triangle. Now, for electromagnetic radio waves in space or air, the velocity in a vacuum or air is always the speed of light, and that makes things a bit simpler for us. The velocity is slower in other mediums, but we're only considering air or vacuum because the radio waves that we send out, whether they're on VHF or HF, as we transmit our signals, always go out over an air or a vacuum. So we don't really need the triangle. Let's see why. Well, for radio waves in a vacuum or in air, V equals F lambda, we don't need that. We already know what V equals. It equals the speed of light. In other words, 300 million meters per second, or putting it another way, 3 times 10 to the 8th meters per second. Looking at the equation below, well, we can substitute V, we can put in 3 times 10 to the 8th meters per second. And the same for the one F equals V over lambda. We can just say F equals 3 times 10 to the 8th meters per second. So really, we've only got 2 equations, and those are the 2 shown there. Now for the foundation exam, because we only have 2 variables, now we only have lambda and F, we can simply plot one against the other, or use a plot that somebody else has done. And this is the plot that you get in the foundation exam. This is part of the sheet that you're given and you're able to refer to answer the questions in the foundation exam. And wavelength is plotted on the vertical axis there, and frequency on the horizontal axis. Maybe it'll be more simple or clearer if I give you an example. So the foundation exam uses this chart, and the question might be, what is the wavelength of a radio signal with a frequency of 30 megahertz? Well, we simply locate 30 on the bottom axis, there it is between 20 and 40, and draw a line up vertically to intersect with the plot. And at that intersection point, we then draw a line over to the wavelength axis, and it arrives at 10. So you can see then the answer is 10 meters. So the answer then of what is the wavelength of a radio signal with a frequency of 30 megahertz, the answer is 10. Then on the bottom of the screen, you can also see using the triangle. Lambda equals V over F. If we cover up lambda, we see that it equals V over F is equal to 3 times 10 to the 8th over 30 times 10 to the 6th. Now, don't worry if you don't understand this scientific notation. This all becomes clearer in the intermediate and in the advanced courses. But if you do evaluate that, you come up with 10 meters, the same answer, as you might expect. So there's 2 ways then of converting wavelength to frequency. One is to use the triangle and plug the numbers into a calculator, and the other is to use the supplied chart, which is supplied for you in the foundation examination. Let's look at another example. For this first example, we had the wavelength and we had to determine the frequency. Let's see what the frequency is if we are given the wavelength. So here we're given a wavelength of 20 meters, and the question says, what is the frequency of a radio signal with a wavelength of 20 meters? Well, this time we start on the wavelength axis because that's the information we're given, and we locate 20 on the left. And we draw a line across horizontally till we intersect with the slope of the graph. And at that intersection point, we draw a line down vertically. And the answer is then 15 megahertz. Now, you might say, well, I can see it's between 10 and 20 megahertz. I can't determine exactly that it's 15. If you're given a question like this in the foundation examination, remember it is multi-choice and the answers will be spaced out far enough so that there's obviously only one right answer. You can also do this with the V equals F lambda equation, and for this one you would use F equals 3 times 10 to the 8th over lambda. So there we have it. That just about covers radio waves. Remember, this is part of the background series, and don't get too dispirited if some of it seems a bit perhaps difficult or a bit abstract. It's only for background for those that are interested. Thank you very much.